Okay, welcome back to class, everybody. It's a pretty good time to get started. So let's just briefly review what we discussed last time. So we started with some of your questions on homework 4, and then I introduced homework 5 to you. So in homework 5, you're going to implement basically the equivalent of Google Maps, where you can route a person from one address in Austin to another address in Austin, obeying, for example, the various directions of traffic. Then we finished the facility location example that we had. In particular, we turned our sort of just script code into a nice class that you could easily extend and change, that just sort of took in data files that specified the problem and could output a solution. And we never got to minimum spanning tree. So today we're going to do minimum spanning tree a little bit later in the class. But the plan for today is first to just begin with your questions and some administrative discussion on what's going to happen in class over the next few weeks. Then I'd like to go over the code for homework 4. So homework 4 is due today. I checked before class, and maybe a fourth of you have turned it in, so not very many. But at the same time, I'd like to point this out, that late last week I had people coming and asking me questions about homework 4 that showed it was clear that the person had not even started it, right? So even though we had like multiple extensions of this thing, like there were people in class who still hadn't started it late last week. And so that makes me not feel bad at all that it's due today, okay? So it's due today, and we're going to move on, and we don't have very much time for the rest of the homework assignments. Homework 5 is not too bad. I think that you guys could finish that in a week. But homework 6 is difficult, okay? And so we're going to talk a little bit about homework 6 later today. So that's the plan for today. Go over homework 4, do the minimum spanning tree problem, which is a significantly different kind of solution than facility location or shortest path, which we did before. Talk about homework 6, which is up online, and I'll talk a little bit about how to prepare for that. And then I don't think we're going to get done with all of this, but if we do, we're going to talk about how to scrape data from web pages. So what I mean by that is a lot of times you want to do analysis on data that's on a web page, but it's not like the web page doesn't provide it to you in a nice format. They don't give you a nice CSV that you can load into pandas or something like that. And so there are tools out there that can take that unstructured or sort of web-based data, and you write a small program that then turns it into a nice data set you could do analysis on, okay? So we'll learn a little bit about that. So before we jump into today's material, I'd just like to start with any of your questions, either on homework 4 or on homework 5. Okay, if you don't have questions on that, I want to just briefly, administratively kind of plan out what we have going on in the rest of the semester. So today, homework 4 is due and homework 5 is out. And homework 5 is due next Tuesday when homework 6 goes out. And then you have about a week and a half to do homework 6, okay? And after that, essentially immediately we have the exam and then project presentations. Now, homework 6 is probably, I'd say, maybe as difficult as homework 4 was, like roughly the same order of magnitude, though very, very different. Especially for the people that are giving project presentations towards the beginning, this might be kind of a tight timeline. So one of the things that I've done in class previously is just move the due date for homework 6 to the end of the semester, okay? So what that does is it allows you to kind of pick which you do when, right? If you want to focus on your project first and sort of spend a bunch of time on that before the project presentations and then do homework 6, or do homework 6 first and then your projects. But one of the things that I want to highly, highly caution you against is being like that person who talked to me who hadn't started the assignment, last week. Like, homework 6 is hard. Start it as early as you can to make sure that you get it done. So another piece of administrative things. So no class on Thursday. Instead, I'm going to post a video with some really useful instruction, kind of the same way that I post videos here. That's going to help you with some aspects of homework 6. and also teach you some new things about Python and pandas that you didn't know beforehand, okay? So watch that video instead of coming to lecture on Thursday.
You mean this Thursday?
Yeah, this Thursday. Okay, so unless there's any questions, I'm just going to move on to looking at going over my code for homework 4. And as I'm going over it, I'd really sort of appreciate any discussions or question that you guys might have from the coding that you did. So I briefly looked over a few of the homework assignments that were turned in, and there was a wide variety of how people implemented things. So I'm just curious on your thought process and how it was similar or different to mine. So we can take a look at the files that I have here. And let's just start with the beginning part of the homework assignment, which was this mnist.py, which just had the k-means and the multinomial classifiers. Okay, so I'm importing various things over here, and this is probably cut-pasted from a previous file. So it's somewhat bad style, because I don't think that anywhere in this file do I use collections, for example, right? And typically you shouldn't import modules that you're not going to use. So let me just very quickly see if I use collections anywhere. I don't, so I should take that out. Let's see if I use itertools anywhere. I don't. But SGD I probably do, and PyLab for drawing, and the others I probably all use. Okay, so let's take a look at the Mnist Dataset class. So this was the basic class to let you kind of read in the dataset and visualize various images from it that then you could also use to visualize your gradients. So in the init here, I imported gzip and cpickle, and then read in the data set and store that on this particular object. Except I might have another parameter, which is the data set range. So why do I have this parameter, the data set range? That's right. It's for parallelization, when we're going to parallelize later, right? It's because when we parallelize, I want to read in only like the first fourth of the data set or the second fourth of the data set and so forth. So if data set range is none, I'm going to take in the whole thing. Otherwise, the training set is the data set, but only over the range that's specified, right? So that makes sure that I'm reading in only the first fourth or the second fourth or what have you. And the validation and test data sets, they always get read in completely. Okay, so that's the second part.
Even if DS range is none, you don't need the if else statement. Even if it's none, it will pull the whole data.
So right, so I always read in the whole data from the file, but I don't store it all in memory, right? So at the end of this, like train is either the first fourth, but all of train doesn't actually get stored.
What I'm saying is that cells.train, like if DS range is none, you are taking the whole data, right? Cells.ds0.
Yep.
Even if it's none, you don't need the if else statement. You could just directly write this line, and if DS range is none, it will actually pull the whole thing.
Okay, so that's also possible. But for me, DS range is a slice, and I'm not exactly sure how slicing with none works, if that actually gives you the whole thing or not. Okay, it does? Okay. So that's great. So other things about this function is, some of you ask me sometimes about why do I do the imports here versus up there. So I do that only if this import is kind of needed only in this function, right? Because somebody might be using this class but not the Mnist dataset object, right? And in that case, they can import the module without importing these things. But it's really kind of up to you where you put those imports. Okay, so let's take a look at plot digit. So my plot digit took in sort of a digit, which is just an array with 784 values. So over here, we're going to reshape that array. And I had two ways of plotting it. So one was that grayscale image, which you saw in the write-up, and the other was the color image, which you saw. And that's what the second parameter does, which is just are there negative values or not, right? Do I want to use just a grayscale plotter, or do I want to use the color plotter? And if there's no negative values, then I use the grayscale plotter. And if there are negative values, I set a limit, and then I use the color plotter. Okay, but other than that, I think you're pretty familiar with IAMShow from previous homeworks we've had. Here is just a little helper function that lets you plot a particular index in the data set. So you just pass in an index, and it just calls plot digit on that particular image. And then getSlice, which returns a slice from a data set. So dsName. So here's something that you may not have seen before. So dsName is going to be a string, like one of train, test, or validate. Those are the three types of data sets that I had stored on self, right? And this is a slice object that says how far or how big of a slice you want. The piece that you may not have seen before is getAttribute. So some of you may have read about this online, but what it does is you pass in an object and you pass in a string, and this is the equivalent of doing that object dot this string. So it's the equivalent of doing like self.train if dsName is train, okay? So this is kind of a nice way to programmatically sort of replace the dot whatever, okay? So this way I could say getSlice, train, and then pass in a slice, and it'll return a slice from the training data set. Or I could say getSlice, test with some slice, and it'll return a slice from the test data set. And then over here it just returns that particular slice. Okay, so then we have this Mnist classifier base. So in the homework assignment, I gave you this structure, but can somebody explain why this class exists? Like, why don't we just have the Mnist squared loss and Mnist multinomial loss classes?
It's generic to have the same functionality, but you can put in different blocks.
Yeah, exactly. There's a lot of repeat code between those two classes. And one general rule of programming in a nice format is to not repeat code if at all possible. And the reason for that is that you might want to go and make that code better, right? And if you've repeated it a bunch of times, now you have to make it better in like 30 places instead of just the one place. So generally don't repeat code, and that's the purpose of this class, is to not repeat code between different kinds of classifiers that we might have. Okay, so let's read through what it does. So it takes in a data set, and if one is not provided, it's just going to use a default Mnist dataset. So then we have this function error indicator. So it returns the number of misclassifications on data if the parameters are specified by X. The array X gives the parameters for all categories. If data is none, then count the number of misclassifications on the validation data set. Okay, so if data is none, then we're just going to pull out the validation data set from our data set. And then here is where we use the fact that we're going to be subclassing this class, right? That we're going to be creating derived classes. So this is a general classifier. It doesn't know actually what the classifier is doing to classify this example, right? And all of that knowledge is going to be contained in this classify function, which we're going to re-implement classifier by classifier, because that code doesn't get repeated from one classifier to another. Okay, so here we just classify. That gives us the answer, and then we're just summing how many of those labels are different from the data's true labels, right? And that's what's going to get returned. So Feval is going to just return the function value, and we might average it or not. And so here we're just calling funcEval, which is another one of those functions that we're going to be implementing later, right? Depending on what subclass we have. We pass in some parameters. We pass in this data set that we're going to be evaluating the function on. And then whether we average or not, we're going to average or not. Okay, stochastic function eval looks very similar, except at the beginning, we're going to pick a random subset of the training data sets on which to evaluate the function. So here are the indices. We're picking some random indices between 0 and the length of the training data set, and then that's what we pass into func_eval, okay? So I want to sort of tell you how I came about this structure. It's because I actually started implementing as two separate classes. I noticed that there was a lot of code overlap between those classes, and then I actually created the structure of the base classifier class and the two other ones. So it's something that you shouldn't at all feel uncomfortable doing as you're implementing a project, to like restructure your code in a nicer way that makes it easier for you to debug and like removes overlaps and repetitions, okay? So that's why you have this sort of odd function, func_eval, that takes in some parameters and then sort of a piece of a data set to actually evaluate the function. So grad and sgrad look very similar, except they're calling Grad Eval instead. And at the end of sgrad, we're going to bound the gradient if we need to, because we need that for stochastic gradient descent. And then these functions don't do anything, right? Classify, func_eval, and Grad Eval, they're empty at this point because this is a generic classifier, and those are the three that we're going to implement specific to the individual classifiers that we have. Okay, so let's take a look at my squared loss classifier. And so this is where, I'm curious on how you thought about implementing these functions and how differently they worked in mine. So for classify for Mnist, what we have to do is we have our various parameters, and for each data point, we have to see which of the parameters is closest, right? And so that's what I'm doing here. First, reshaping the X into the 10 different categories, so I can pull out the various categories. I'm going to keep a minimum distance, right? So for each one of the data points, it has the distance to the minimum category and which category that is. So that's what these two arrays are. And here I'm iterating over the 10 values, basically saying what's the distance from that center of all of the points. And if that distance is less than the minimum distance, then that, for all the points where I've found a distance that's less than their previous minimum distance, their category gets updated and their minimum distance gets updated, and then I return the category array, okay? So that's how I did it. It has a for loop. Probably there's a way of also doing this in a broadcasting way. Yeah.
So the way I did it was similar, but I just took, so I'm looking at the distance, but calculating the distance through all 50,000 points or whatever. You have a 10 by 784 minus a 1 by 784 as you're going through all these images. Mm-hmm. And then you just calculate the minimum argument.
Yeah. So you used,
return.
That's right. So you used argmin to substitute this for loop.
That's right.
And I think that's fantastic. Yeah. And works, yeah, very nice. So what's the main difference? It's a much faster for loop than what I have. Because it's in C. That's right. And if we have some time later in class, I'll show you guys how to actually insert C code in Python. So it's possible to make Python code like that fast also. But let me ask you this question. So mine is slower. What advantage does mine have? That's right. That's the only advantage, right? Because that's right. Because that one computes like 10 distances and then does the argmin. Well, this one at any given time has at most 2 of them, right? The most recent one and the minimum one.
Mine ran a little faster than the.
Yeah, that's great. That's great.
Is yours working in a vectorized fashion?
So classify does not work in a vectorized fashion. So I didn't make my classify functions work in a vectorized fashion. So in particular, what would have to happen for classify to work in vectorized fashion is if I passed in 2 x's, right? Then I would have to get out 2 categories, one for each of the x's.
Okay, so maybe my question is, the data is potentially, it's more than one image?
Oh yeah, so data could be like 50,000 images, right? But x, and with this code, x can only be one set of parameters. Right. Okay, so this was a function that sort of returns a class order, and this is, I think, interesting, right? Which is a classifier doesn't only tell you which class like a particular image belongs to, but actually could order all the classes, right? It could tell you like this is the one I think it's most likely, but hey, you know, it could be this or it could be that. And there's sort of numbers associated with each one, so you can know when it's a close call between two categories and when it's not, right? So that's what class order does. You pass in just a single image and a bunch of parameters, and just going to return the class order for that image. So this is something I used for debugging when I was implementing my code at the beginning to see like why my classifier was making errors on certain images, okay? And probably something just useful to remember in general for multi-category classifiers, that you can get out category orders out of them as well. Okay, so let's take a look at func eval. So here now we get a bunch of parameters and a bunch of data. And so now this is vectorized in the sense that you said. I could be getting like multiple parameter values and like 50,000 data points. And we're going to return multiple function evaluations, one for each of the parameter values. And the main thing that tells you the difference between the two functions is this reshape call, right? So here I'm reshaping it based on how many ever x's I got passed in, and then 10, 784, versus previously, which was just 10 and 784. Okay, so then what's going on in the next call is I have to match up the appropriate W with the right image, right? So each image has a label on it. And for our function, we have to take the parameters that correspond to that label and subtract it from the image data. That's right. And so that's what this call to take does. Here I'm using the labels, and I'm taking the W pieces dependent on those labels, right? And axis equals 1 lets me do this take along this axis, right? Along this 10-dimensional axis. And so the rest of it is going to stay the same. And then here we do data minus W's, and then answer is equal to the sum of this times itself. And then I'm summing over just axis 1 and 2, right? So why am I not summing over axis 0? Because I have two or many sets of parameters, and I need to return many sums, one for each one of them. Okay. So I think maybe the most interesting parts here is the usage of take, and maybe this usage of sum with multiple axes. And so any comments or discussion in terms of how you did it versus this code? So what does map do?
I mean, it iterates over the different points that you're iterating, basically. So we did func eval for each point, and then that.
Okay, so is map basically a for loop though?
It basically is.
Okay, so like not quite vectorized in the way that we want it to be vectorized, right? So what I suggest doing in that case is just spend some time to like think through the indices or like the array dimensions here. I think it's just something that's going to be useful, right? Yes, another question. Oh, why am I using take?
We just index it by the data like X.
So say what you want to do.
So I just did X of data 1, like the labels minus data 0, and then
okay. Okay, so X of data 1 basically probably does take in the right way, right? So it's likely equivalent, it's probably doing the exact same thing. Though it's possible that they might be different in terms of running time. So it's something that I'm not quite clear about. So that's another kind of question that I had for you all, which you can tell me maybe towards the end, as I'm curious kind of how your running times compare to what you saw in my printout, especially for parallelization versus not. but also the other ones as well. Okay, so let's take a look at Grad Eval. Yeah.
So you have assumed that the x is like 7840 vector. So we
Yeah.
can also assume it's 10 cross 784 and path when you are calling the function path in that shape.
Sure. Yeah, you can do it however you want. For me, the parameters are just like 7,840 long vector. Yeah. Okay, so let's take a look at Grad Eval, which looks very similar to F Eval, right? So here I have my x, which I'm going to reshape again in the same way as before. But now I'm going to use a, let's see, W index. So this was something that we talked a little bit about previously, and it's because of, I'm going to use ND image sum later, right? And so I need to match up sort of which part of the sum needs to go where. Does that ring a bell from our previous discussion? So ND image sum needs some labels. It needs to know sort of which sum should go to which part of the vector. And so what these indices are doing is they're the labels that we're going to get. So how big of a gradient am I going to return? Well, I'm going to return a gradient who's going to have as many spots as x does, right? And that's what this A range does, is it creates as many labels as there are spots in X. So that's X shaped 0 times 10 times 784. And then I reshape those labels so that they look exactly the same as the W's. So now the W's and their label positions are kind of parallel arrays that I can use for my computation. Okay, so here I use take to do the same operation on the W's and the labels, which is again sort of matching them up with the right pieces of the data. Here we're doing our gradient calculation, data 0 minus WS times minus 2. And then here's the ND image sum that's taking that and then these labels and then is going to produce the entire set of sums, okay? And then that gets returned as the gradient reshaped appropriately. So the shape is, it has as many rows as x dot shaped as 0 has, and then 10 times 784 for the second dimension. Does that make sense? Okay, so again, based on comments that you guys had in class previously, I think this was one of the most difficult parts of this assignment. It's just kind of thinking through the vectorization and the broadcasting that's happening inside of these Grad Eval functions. Okay, so let's take a look at the multinomial logistic classifier. So again here, we're going to have to classify some data that's given to us. So we reshape the parameters as before, but now we're going to have a different kind of objective function. But my computation works the same as before. So I'm going to compute a negative log likelihood. Okay, so when you did your classify function, did you guys compute the e to the something over the denominator or not? How did you do it? That's right. So when you do the argument that's in the exponent, what you're doing is you're kind of computing a log likelihood, right? So when you think about taking the log of that probability expression, what's going to happen? First, the denominator is the same for all the classes, so that kind of goes off to the side and it's some constant, right? Then you have just that exponent argument, which is w times whatever the data is, times log of some other constant, right? So the only thing that's going to differentiate the classes is that negative log likelihood, right? So that's what I've set up here is the same way that we had a distance array before. We have a negative log likelihood array, which starts out as infinities, and then a similar kind of for loop computing these dot products with each one of the w's and storing a new category if a new category is warranted, okay? And then I return the categories at the bottom. So again, you may have done it differently. You may have sort of used argmin or something like that, or argmax. Yeah.
I have a question about this is for classification, right?
That's right.
So why do you have to calculate the logarithm, the log, because again based on this one?
So what I'm doing is equivalent. It's the same. So it's just a log transformation of that fraction, right? So if you computed that fraction, it's going to give you the same categories as what this gives.
I only calculate the
Numerator.
only.
Okay, so you're just taking the exponent of whatever it is that I've calculated, but totally equivalent categories are going to result. Okay, so then class order does the same thing as before. It's just useful for debugging. So then let's take a look at func eval, which is now actually going to compute that negative log likelihood that we minimize with our stochastic gradient descent. Okay, so at the beginning, a similar kind of reshape as before. And this was something that I mentioned when we were discussing previously. So I got an out-of-memory error in this function if I pass in a data set that has more than 500 images, okay? So here I have an if statement that if I have less than 500 images, I'm going to use some vectorized code, and otherwise I'm going to use a for loop, okay? So if I have less than 500 images, my function here first computes the second part of the function expression, right? So that's the log of the sums of the exponents and so forth. And so that's what's happening here. So the denominators are the exponents of the data reshaped to an appropriate shape, dot producted with the w's summed along axis 3, okay? So that's kind of that 1 over e to the wi dot ak. So that's what the denominators here are, and then we're going to take the logs of those denominators. So otherwise, we're going to compute these denominators with a for loop that basically does the same thing. Okay, so once I have the denominators, I can compute the whole function, which the first part of it has that dot product of the data and the w's, which happens here, and then we have the second part, which is the denominators we computed, and then we return the sum of that function. Okay, so any questions or differences or similarities to how you did it? So my question is, how many of you used a piece of paper and a pen to kind of think through the dimensions? Oh yeah, like I definitely did, right? And in fact, I think in the next function, you'll see that I even kept it as, so maybe I didn't. But at one point, so not in the current version of my code, but at one point in my code, I had comments here that sort of listed the dimensions of each one of the arrays, so that I could go through in my mind exactly like what for loops are happening with each one of these calls, okay? And I saw maybe one or two of you did something similar when you turned in your code. So totally the appropriate thing to do. Okay, so let's take a look at Grad Eval. So again, we're going to use ndImageSum at the end to kind of match up the sums with the appropriate parts. And so the first part of this does exactly the same thing as setting up the labels that we had done previously. Right, so first reshape the x's to an appropriate shape, create the labels and reshape them, and then use take to match up the w's with the right parts of the data and the labels with the right parts of the data. Then we're going to compute the second part of the summand, which is that part that had the logs and so forth. So that's what's happening here. So yeah, so here we're computing 1 over the exponents summed, reshaped in the appropriate way, times the exponent dotted, and then the second summand is those coefficients times the data with an appropriate reshape. Okay, so again, I don't think that this is something that can be absorbed by just looking at that line of code for 3 seconds. Okay, it's something that probably requires some pencil and paper, sitting down and thinking through it. And as an exercise, it's probably worth it to kind of see how similar or different your vectorization code is to this. More to give you experience in reading somebody else's code. So the same as all the other assignments, I'm also going to assign some peer reviews online, so you get a chance to look at some other people's code in class to see how that's similar or different to your code. Okay, so that creates all the various classes that we need, and the rest of this file actually just executes creating the images and so forth. So here we plot the first digit, we plot the squared loss gradient as I discussed in class. So one of you had asked me about whether this was an error in my write-up, and I probably just cut-pasted it from my code, right? So I executed vectorized grad eval, and here I'm just taking the first part of the gradient to actually plot. So it basically shouldn't matter whether it's vectorized or not. So the next part is actually doing the evaluation for the squared loss error and the multinomial loss error. And so we had a question about this some time ago also about the usage of timeit. So this is how I use that. So I just record the start time in seconds by using the default timer. I record the elapsed time by looking at the default timer again minus the start time, and then that's what I print out. So just like 2 calls to timeit that record the seconds.
What's the benefit of using, I didn't use default timer, I was trying to use a more less intuitive function on timer where you can call the function and see how long it takes and just output the time. But using time like this, what's the benefit of using timeit over just time?
There isn't. It's the same. They just return seconds count. Okay. That's it. Yeah, that's right. That just returned kind of the seconds time. Yeah. Okay, so just some feedback from you in terms of your experience in testing these classifiers. So I'm curious what kind of error rates you got for classification, and also what kind of timings you got for testing your code.
I got pretty much the same error rate, just a little faster.
Okay, fantastic. Fantastic.
But the time for the payment is less than you.
Okay.
But for the second part, multinomial is like 1.5 times slower.
Okay, so if you see large timing differences, okay, it's probably worth it to do that comparison of my function to your function. So maybe I'll even post this code on Canvas so you guys can sort of download it and take a look at it and compare against your code, because there might be some educational benefit to comparing timings, especially if you're getting faster or slower. So if you're getting faster time, I'm curious sort of where my code is crappy, right? It's probably in that for loop. Other questions?
Code with lots of for loops, and I have much faster time here.
Okay, so the other thing is there's laptop differences, right? So just that what we're recording is like wall clock time and not sort of like chip execution. And so one thing that you might do if and when I post this code online is sort of run mine and yours on your laptop, so you're comparing them on the same machine. And then it's still possible that you're getting something faster because maybe my code wastes a lot of time in memory allocation and deallocation. So there's many ways in which code can be slow. And if we have some time later in class, kind of depending on how our lectures go, in the same part that I teach you about how to insert C code in Python, there's some other tools that can make Python just outrageously fast, okay? But it'll still look like Python code. Okay, so that's everything that I wanted to say about this part of the assignment. So any questions before we move on to parallelization? Okay, so let's take a look at parallelization then.
Professor?
Yeah.
When you do the SDG part, did you pass the average this parameter to be true or false? Because your default is true, but actually when I choose to choose, I have very high error rate.
So I probably am using the default because SGD doesn't actually pass in any extra parameters to SGrad. So I'm using the default of true, and so my code is definitely averaging when it's computing those things.
Because I passed 4, then I got the almost same error rate as you.
Okay, so it's worth investigating as to why that is. So it's possible that something's going on in your averaging that you don't expect. Okay, so let's take a look at the parallelization part. So in this part, the first bit is to set up several engines and to have each engine read in a different section of the training data set, right? And the way that we're going to do that is by executing this function that we're going to call engine object setup on each one of the engines. But this function is going to have different arguments on different engines, right? So on engine 1, it's going to have, the parameter 1 and total 4 engines if I have 4 engines. On engine 2, it's going to have engine 2 and total 4 engines and so forth. Okay, so I have a bunch of imports after that. I'm going to print out the engine ID, which most of the time you're not going to see because it's happening on some engine that's not the client's engine. Then I compute the data size, which is 50,000 over my total number of engines, how much ever that is. So if I start the cluster with 5 engines, I'm going to get a fifth of the data set on each one of the engines instead of a fourth, and so forth. And then here is where I'm going to read in a data set. So engine data store is just basically an empty module that's going to store all the data that we're going to read into the various engines. So if you look at the engine data store module, there's nothing there. It's just empty, right? But in this line, in engine data store .ds, what I'm doing is I'm creating a little Mnist Dataset object inside of that module, right? So now when my parallelization code goes back and imports this module again, this data set object is going to be there. And this data set object now gets a DS range that has a slice that sort of tells me which part of the data set I'm supposed to take out. Does that make sense?
Well, so I can already tell that maybe part of the reason my parallelization code is lower than my non-parallelization parallel code. I must have just misunderstood what you said because I thought we were supposed to randomly send a slice of data to each of these.
Oh, so you're sending the data
Well,
from
no,
the client to the
I'm
engine.
doing the data store the same way, but the slices are broken up randomly rather than being divided.
Okay, so there is going to be randomization like that, but it's going to happen in SGrad. So when SGrad, that's right, when SGrad calls these, and with 200 samples or whatever, those samples are going to get uniformly distributed across the engines.
Okay.
But each engine sort of takes a contiguous piece of the data set.
Right. Okay.
So why doesn't it matter? Why doesn't it matter that I'm not randomizing which section of the data set each engine is taking? It's because the fact that SGrad is doing things randomly is going to return the exact same probability distribution over examples as what you did.
Okay.
Because each example has the same probability of getting chosen, like in either case. Does that make sense?
Well, I ended up doing, I did it both ways. I had random slices and used splitting calls on
Okay.
That might be why it was lower.
Yeah. Okay. So anyway, so here we set up these data sets. And then the second important part is that I'm going to create the loss object, right? So this is going to be the multinomial logistic loss. And that loss object is going to work only on the data set that's inside of this engine, right? So that loss object doesn't have access to the whole data set. It only has access to the 1/4 or 1/5 or whatever that got read into this engine. Make sense? Okay. So let's read apply loss function, which is another function that we're going to be sending to the various engines. So this is going to tell this loss object to do something like sgrad or sfeval or something like that. So apply loss function, it imports engine data store. An engine data store at this point is going to have both the data set and the loss object in it. And here I'm using the same get attribute which you saw previously, right? So here I'm calling get attribute of engine data store.loss with that particular name, which might be something like sfeval, right? So this would be engine data store.loss sgrad or something like that. And then here I'm passing in the function arguments and keyword arguments. So that's the way that I can be calling the sgrad of all of these loss objects on all the engines simultaneously. Okay? Okay, so the next is a little helper function that's going to help me split my 200 data sets or my 200 samples uniformly randomly across the 4 engines. And this works like we talked about in class. So I pick a bunch of numbers that are uniformly random between 0 and how many ever samples I'm going to take. Then I sort, and then that tells me how many calls to give to each one of the engines. Okay, so I hope that all of you had a function like this somewhere in your code. Okay, so then let's take a look at the actual parallel loss class. So the parallel loss class is going to take client, which is going to be the thing that communicates with all of the engines, right? So it takes a client, it creates a direct view, and then it's just going to store the total number of engines in a little variable, n engines. So when you call classify, this class doesn't know anything about what the classifier does, okay? So my classify, what it does is it goes to the 0th engine and calls classify on that engine, passing in this X and that data, okay? Then gets the answer and clears the results from the client and returns that answer. So in this way, parallel loss could work with the k-means classifier just as well as it could with the multinomial logistic one, because it's just using the functions that are on the engines as opposed to implementing anything of its own. Okay. So error end works in a similar way that just calls classify. So then let's take a look at sgrad. And I hope that your parallel sgrad looked very similar to this. Okay, so let's see how this looks. So I have a results array, which is going to start as just an empty array. Then I have a for loop that's looping over the engines, right? So this is going to give me a list of engines, engine 0, 1, 2, 3, 4. And then it's also going to loop over how many pieces of data I want from that engine. So if I had 200 total calls, this is going to split it into 4 engines or whatever, so that I'm going to be getting 75 from the first one, 100 from the second one, and so forth. Make sense? So that's the engine that I'm going to call, and this is the number of data points that I want from that engine. And so in here, it's if I'm going to select any data from that engine at all, then I'm going to do a call. And if I'm not going to select any data from that engine, it's not worth it for me to send it anything. So then let's look at the call. So this is the call. It's a dv.apply. So I'm going to apply this loss function. In particular, I'm going to call sgrad of the loss object that's on that engine with that x, this number of data points, bound equals false, and average equals false. so that I can do the summing at the end here in the parallel code. Doing this for loop appends these asynchronous result objects to the result list. And then in another for loop, I'm getting all of those objects. So temp here is one of the results from one of the engines, and then I'm adding all those results and answer, clearing everything from the client, and returning the bounded gradient of answer divided by the number of data points that I have. Does that make sense? And is that similar to what you did for your parallelization, right? So the key here is that we're going to use asynchronous results. So why doesn't the following work? So what's bad about putting this r.get like right there?
It likely won't have, an engine might not have returned a result. Basically, it might not have finished working.
So I'm actually losing the entire point of parallelization if I do the r.get here.
Oh, I see.
Because what I'm doing is I'm sending a call to engine 0, waiting for that call to be done, sending a call to engine 1, waiting for that to be done, and so forth, right? Well, here, I'm sending out all the calls and then waiting for all of them to be done at the same time. So I'm actually getting parallel execution specifically because there are different for loops here. One that just sends out the calls and gathers the asynchronous result objects, and the second one which gets all the results from the various engines. Does that make sense? Okay. Okay, so once you've seen one of these, all the rest of them look pretty much the same. So for SF eval, it looks really exactly the same. The only thing that's changing is I'm calling SF eval of the loss objects instead of sgrad, right? But again, it has the same structure, a little for loop that sends out the call, and another for loop that collects the results. Okay, and then feval looks similar. And then this is my code that runs everything. So maybe the most interesting bit here is this bit, which does the engine object setup and passes in the different args to the different engines. So this is the number of engines and the engine ID. And it works in the same kind of asynchronous way, right? So I tell each engine to read in its data file, and then here I just collect the results. So why do I collect the results? Why don't I just keep going after this? So, you know, this function doesn't actually return anything meaningful. It just kind of returns 0. So why do I have that for loop that collects the results at the end? What might happen if I don't have that for loop? Yeah, that's right. That's right. So down here, I'll be sending more parallel calls to these engines, right? So I want to make sure that this engine actually did read in the data before I start sending things to the loss function. And so this is really important because I need to wait for all the engines to read in the data, set up all the loss objects before I can actually run the parallel sgrad. Okay, and so this is our parallel sgrad. You set up a parallel loss. You call SGD on this parallel loss, and then you test it. So again, you might get totally different speedups or time differences than me, and I'll post this code online so you can compare it with yours. So just out of curiosity, how many people got a speedup from parallelization? Okay, if you didn't get a speed up, there's probably something wrong, okay? Like, it's worth looking to see why. Like, how many people got a significant slowdown because of parallelization? Like, how much of a slowdown are we talking about? Like, is it like 1.5 or is it like 10?
Like 100 seconds on Multinomial.
Okay, it's worth investigating where that is and why that is, because I don't think that should be happening.
Yeah, really. I wonder if Scott suggested that it might be that I'm playing block, I'm making it block somewhere. Or
It's
maybe
possible.
It's what you mentioned a minute ago, where if you do get in the place where you're.
That's right.
Yeah, there could be that.
So this, what I mentioned, is definitely going to give you slower running times than your serial code.
Right.
So if you call the get right here, because what's happening is you're getting overhead from communicating with the engine, but you're not getting any speed up from doing things in parallel, right? Okay, so one thing that I hope that you think is cool, I certainly thought was kind of cool, which is that we're using the exact same code that we built, like, an assignment and a half ago for stochastic gradient descent. But it's working now in a totally parallelized way with this gigantic data set, just with these two lines of code difference, right? Which is just this one that sets up the parallel loss, and then this one that passes in that parallel loss function to sgrad, right? So the reason that is because we designed our code structure in the right way, right? So that idea of interfaces, which you read about several assignments ago, is really important for structuring your code. So thinking about how one object communicates with another. Because what that does is it lets you just implement the same interface, but an entirely different way of doing it in the back, which can really significantly change what the program is doing. And that's what we did here. We just implemented the sgrad SF eval interface, but now we're doing it in a parallel way instead of the serial way that we did previously. Okay, so any final questions or comments or discussion on homework 4 before we move on to the next topic? Yeah.
So I have a question about the data stored in Engine.
Yeah.
At first, you use like Engine data store module to save the data.
Yeah.
But when you use the apply function, how do you make sure like they are actually using the Engine data store dot data?
Yeah. So let's take a look at those. So that happened at the very beginning of this file. So this is where I set up the data store in the loss object, right? So this is how I'm making sure that I'm using the same one, is that I have the import engine data store call inside of this function. And here I'm referring to the loss object inside of engine data store. So it's going to be the same one that was set up in this line. Does that make sense? Or it seems like you have a follow-up question?
No, I mean, my code is just pretty slow because actually I don't know how to take the data set, like run apply the function using the data set stored in it, so I have to build another like input for the function using the data set.
Okay, so I don't quite understand that comment, but maybe you can just ask after class. But another question, yeah.
For some reason, like I was getting much higher error rate for the multinomial logistic classifier, like double.
Okay.
Errors. And the gradient that the plot of the gradient that you showed in the assignment, I got like the same.
I see.
So
It could be because you're not bounding or you're not averaging in the right way somewhere.
I mean, I have them like both.
So I'm not sure, but given the fact that many folks in class are getting the same error rates as me, there's probably a bug somewhere in your code.
I played with the step size. I got drastically different results.
Okay, that's interesting. So what changes did you do on step size?
I found 50 gave me the best value. Like yours had 100, but I tried like 10, 20, 1.1. But if I did 50, like my error, like my classifier did like way better.
Okay, that's interesting. And what were your initial condition points?
This is a random one.
Okay. Okay, so this is kind of some useful discussion, and it's a bug that I had in my code, which is let's take a look at the initial conditions here. So here my initial conditions are picking 3 uniformly random directions in 7,000 dimensional space, right? So if this was rand and I was picked uniformly random points in 7,000 dimensional cube, okay, instead of uniformly random directions, what's the problem with that? Like, why?
You get more in the corners or whatever, right?
So that's certainly one issue, is I'm going to get more in the corners, but it's more of an issue that's related to the step size discussion. That's why I bring it up. So what's the distance from the corner of a 7,000 dimensional cube and 0? But how long is it, like roughly? Yeah, like square root of like 7,000, right? And so the point is that as you change the dimension, how far you're getting away from 0 when you're picking uniformly random points in a cube, it gets like farther and farther away, right? And for SGRAD to work, you have to be like reasonably close to where the optimal is, right? In our proof of SGRAD, one of the things was how far away the initial point was from the optimal point, right? So that kind of determined the step sizes. And so that's why sort of using 0 or using one of these uniformly random directions is a better initial condition than using something on the square. And when I use something on the square, I got much worse classification results.
You're just going to get 1 for a lot more of your SGRAD for more steps, right? Because it's going to sort of force it into the right spot eventually with
Oh,
SGRAD.
yeah, it's going to force it into the right step, but I might need way more steps, right? Or like a different step size, like a much larger step size, perhaps.
I mean, I did try to play with the step size, but it didn't work.
Okay, it's probably a bug somewhere else. But, good comment on the step size. It's not something that I tried with my code. And out of curiosity, like what's the best error rate that you were able to get?
It wasn't, I have it. Yeah, like, it was comparable, it was just relative to other ones.
Okay.
Like significantly worse ones for other step sizes. So like 1133 error, so I think that wasn't as good.
Okay. Okay. So one last comment before we move on to our next topic, unless you guys have questions, is there's many other classifiers that you can train with stochastic gradient descent. So I just picked a couple, but there's other ones like support vector machines is a very common one that you might have heard before. So that's something that you also train with stochastic gradient descent, okay? And lots of other ones. And so we could have sort of like kept doing homework assignment after homework assignment where we just implement different classifiers, right? But you're not going to learn very much other than like a new objective function and a new gradient, right? Okay, other questions about this before I move on?
I was just going to say, if you're trying to debug your parallel code, I figured out that you can run the debugger through this. So you do %run -d and then have your file name. Because just running the parallel code, like you said during the lecture, you don't get nearly as helpful of error messages.
Yeah.
So you'll get those error messages if you do %run -d, and it'll go through the code like you're doing it.
Fantastic. Yeah, and that's because we're using IPython's built-in parallel code. So IPython has a bunch of functionality built into it to make it work really nicely with this kind of parallelization, the IPython.parallel parallelization. So I never used that, but it's very cool that you used it and you found it useful and you read about it online. So that's like exactly the kind of thing that I'm hoping you guys get out of this class, is the ability to find tools like that yourself and use those tools. Okay.
By the way, numpy.txt seems to be faster.
Okay, so interesting.
But not like they are the same order. Like numpy.take takes around 900 nanoseconds, but the other one takes 940 nanoseconds.
Okay. So I'm not surprised that roughly the same order, but some SciPy functions will be significantly slower than others, right? So just because it's one line doesn't mean that it's fast. So be careful with those things. So the last thing, or going back to what we talked about, what we've been talking about in class recently, so sort of interspersed with our discussion of homework assignments, we've been doing various examples of PyOMO. So now you guys know how to implement objective functions and constraints and so forth. But I want to do one more example that's a slightly different and maybe more interesting way of using PyOMO, which is to solve the minimum spanning tree problem. So those that are not familiar with minimum spanning tree, let me explain it using an example here from Wikipedia. So somebody gives me a graph like this. Let's just imagine that it's a undirected graph like this one. A spanning tree is a subgraph, meaning that I have to select certain edges from that original graph, but not all of them. And I want that subgraph to not have any cycles in it, right? So I don't want any way for me to sort of like go around in a circle with the edges that I've selected. And I also want, when I add up the weights of these edges, that's kind of the minimum possible value out of all graphs that don't have cycles. So a graph that doesn't have a cycle is called a tree, and the sum of these numbers is called the weight of the tree, right? So minimum spanning tree just says, give me the tree that has minimum weight whose edges touch all of the nodes in the original graph, okay? So in this example, these are the edges, and they've shown two graphs that are both minimum spanning trees of this graph, okay? So our goal is to create a integer program that we're going to solve with PyOMO to solve the minimum spanning tree problem. By the way, does somebody already know like a simple algorithm to solve minimum spanning tree? Yeah, Kruskal, Prims, like there's various algorithms that are out there that are not integer programs to solve this. We're not going to do those. We're going to specifically do it with an integer program because it's going to let us learn some things about integer programming. Okay, so let's try to design an integer program to do this. And we're going to do it the same way that we did it with shortest path and with facility location, by writing down an objective function, some sets, some constraints, and so forth, right? So it's for minimum spanning tree. And the important thing here is I have some CIJs, which is the length, or oftentimes people call it the weight for this problem, of edge ij. Right? So that's kind of the data that I'm going to have for minimum spanning tree. So help me start writing an integer program for this problem. So what's the first thing that I might want? Okay, yeah. So what's the how would I write the objective? That's right. So what you did is two things. You wrote down the objective, but you also introduced some variables, right? So what do the yij's actually mean?
We wanted that edge included in the tree and zero otherwise.
Yep. So do we include edge ij? Okay, great. So this is a great start. So minimize some of Cij, Yij's. But if I go and stick this into a solver, what's the answer I'm going to get? 0, right? So I need some constraints that force this to be an actual tree, right? So any idea of how, what kind of constraints I could write down to force it to be a tree?
Some of y's going into the last node after 1.
So the sum of y's, so what do you mean by last node?
Well, if you're trying to get to you're trying to calculate the minimum, or the minimum span between a point and the last one, right?
So all the all the nodes in the graph have to be connected to this spanning tree. So in that sense, there's no order. There's no first and last point.
Sum of 1 should be equal to the node minus 1.
Okay, so this is a great constraint. So let me write it down, and then you can explain why this is a reasonable constraint. So the constraint is the sum of yij's has to equal to n minus 1. Where, what is n? So why is this a constraint?
It will ensure that there is no, it won't
So-
ensure actually, but like for connectedness of all the nodes in it, that there should be at least n minus.
Right, if I want it to be connected, I can't possibly do it with less edges than this, right? And what happens if I have more edges?
Cycle.
It means that I'm going to have a cycle somewhere, right? So that means that if I want a minimum spanning tree, I have to have exactly n minus 1 edges, right? But this is not quite enough.
I need to ensure that there are no subtour.
Yeah, that's right. So here's an example about why this is not quite true. So here's a graph with 4 vertices, right? So I should be able to construct a spanning tree here with 3 edges, right? But one solution that's going to come out of this program is this, right? This is perfectly feasible because I have 3 y's that are 1, but it's not a spanning tree because I have a cycle here and this node is not connected, right? So what you said is exactly sort of the nomenclature that the literature uses for this, which is we need what's called Subtour elimination constraints. That's what people often call them if you look up papers. And what that means is that I have to eliminate possibilities like this. So what's going on here is that I have 3 nodes that have 3 edges between them, right? So given that, can you give me an idea of what other constraint I might add to eliminate this condition here?
For all subsets of the nodes, we'll have to ensure that the number of edges are less than n, I guess.
Yeah. So let me write this down. So let's say that n is my node set. So I'm going to say for all sets S that are a subset of n, right? So this might be like all of them, but one subset is these, another subset is these, another subset is these, right? I'm going to have as many constraints as there are subsets of all the nodes in the graph. And I'm going to look at the sum of the yij's that are in that set, right? So if I don't want a subtour in this set, right? So I'm looking at a particular set. What constraint should I add to eliminate that subtour? Say again?
The number of nodes in that set.
That's right. That's right. Something like that, right? So let's see how that would work here. This is one of our sets, right? It's that set of 3 nodes. But if I look at it right now, if I sum the y's of that are all in that set, then I have 3 nodes and I also have 3 y's, and so this constraint is going to get violated, right? So this isn't going to be feasible. So let's just quickly check if an actual tree is feasible. So this is one kind of minimum spanning, or this is one kind of tree on this graph, right? So let's check now some of these sets. So here is one, right? So I have 3 nodes and 2 edges, so that seems good. Let's do another one. 3 nodes and 2 edges, that seems pretty good. And if you check all of these, they're all going to be good, okay? So here's one with 2 nodes and 1 edge between them, so that's also good. But then here's one with 2 nodes and no edges between them, right? So this doesn't have to be an equality, right? So it's not going to be equals, but it's going to be a less than or equals, okay? And it's possible to prove that this is sufficient, okay? Okay, so we have now an integer program for minimum spanning tree. But can you tell me like why I don't want to go and program this in Pyomo right now? Yeah, so this is a huge problem right here, right? So imagine that I just had a graph with like 20 nodes, right? How many constraints am I going to have here? It's like 2 to the 20th, right? Which is about 1 million, like maybe slightly more than 1 million, okay? And so it's going to take forever for Pyomo to even create this program before it can even pass it to CPlex, and then my computer might run out of memory, okay? So that's the reason that I wanted to do this example, is because instead of solving the whole thing, so what we're going to do is we'll generate constraints sort of a few at a time. So oftentimes people refer to this as row generation. So the reason they call it row generation is you can think of each constraint as a row of a matrix and as each variable as a column of a matrix, right? So what we're going to do is we're going to solve this, but not with all the constraints, just a few. We're just going to like put in a few subsets there. And then we're going to check, is the solution a spanning tree, okay? And if it's not a spanning tree, then I'm going to add a few more constraints that eliminate the solution I just got. And I'm going to solve it again. And if I get a spanning tree out, fantastic, I'm done. And if I don't, I'm going to generate a few more constraints again and resolve it, okay? So can you tell me why, if I don't have all these constraints, but I get a spanning tree out, I've actually found the optimal solution? That's right. It's because if I get a spanning tree out, even if I didn't have all these constraints in there, that solution is going to be feasible to the full program. And I got it from a relaxation of the full program because it had less constraints. So that means it has to be optimal in the full one. Does that make sense? So let's stop here for now. And next time that we get to this, we're going to implement this row generation algorithm in Pyomo. So just as a reminder, no class on Thursday. There's going to be a video online telling you some useful things for homework 6 and for other things in Python. So the one last thing about homework 6 and about getting ready for next week is take a look at homework 6. In homework 6, you're going to have to implement an algorithm from this paper. So it's cited here, an exact algorithm for elementary shortest path problem with resource constraints. Read this paper, okay? Because your final homework assignment is basically, here's a complicated algorithm that somebody wrote about. Like, I want you to implement it in Python. And so you won't be able to do that, and we won't be able to have useful discussions unless you read that paper. So try to do that over the next week, and we'll pick up discussing that paper next Tuesday. Thanks a lot for listening, and I'll see you all next week.